Another important issue to keep in mind when implementing all of these algorithms for fitting mixture models is multimodality. Both the Q function that we use for the EM algorithm and the full posterior distribution, the augmented full posterior distribution that we use to sample using the MCMC algorithm, are typically highly multimodal. And that means that some care needs to be exercised. For example, you need to use multiple initial points. So you should run your algorithm multiple times, every time started in a different place that is random and that are well dispersed. In other words, that they somehow cover the space reasonably well. And the other thing that we need to keep in mind is that some solutions may be numerically unstable. This is particularly the case for the EM algorithm. And these solutions that are numerically unstable are typically not solutions that you really care about because they are going to be very far away from the global optimum. But you still need to be aware that you may find some instability in some of these low value modes. So let's illustrate both of these points using, again, a computer example. To illustrate multimodality issues, let's go back to the IRIS dataset that we had considered previously in this course. If you remember, recall that we ran the algorithm, our clustering algorithm, based on mixture models, 15 times using different initial points just to make sure that we avoided multimodality issues. So in that, when we looked at this example before, we focused just on the best solution. Let's now look at some of the other solutions just to get a sense of how important the multimodality problem is. So the first part of the code that I'm going to run is identical to what we did before. It's just going to run the algorithm, the mixture model algorithm 15 times. And you had access to this code before. So as you remember, this takes a minute or two while it completes the 15 different iterates. And what we will do once the algorithm is complete is to just generate a box plot of the Q values that are achieved by each one of the 15 iterations, just to get a sense of the spread of the solutions. You can see that the execution times for the different iterates can vary substantially, and that's just because the initial points are so different that in some cases you are really close to a local maximum, and in some cases you are not. Okay, so now that the algorithm has completed, this piece of code is just going to construct a box plot for the Q values at convergence for each one of the 15 iterations. And you can see that the values can vary substantially. So remember that this is in the log scale, so a difference of 200 units, roughly speaking, in the log scale is actually a dramatic difference between the solutions. You can see, so in the box plot, this darker line in the middle is the median value of the 15 solutions. So you can see that most of the solutions tend to be pretty close up here, but some of the solutions can be really, really, really bad. So let's look at some of those solutions in a little bit more detail. So first, let me plot the best solution. This is the one that we had identified before, and this is just so that you kind of remember the results that we had obtained. In the optimal solution, so the one with the largest value of the Q function at convergence, you can clearly see that the algorithm is able to separate the three clusters pretty well, and we know that this roughly corresponds to the right clustering clustering structure. So you can see that in particular what we're calling here this group 2 that is in blue is well separated from the other two groups. Now, let's see what happens. So that's the best solution. That's the one that we have picked before. What would have happened if we picked the worst solution? And this is just to illustrate why you really need to do multiple runs and pick the best. So let's say that by chance you run the algorithm and you happen to converge to this mode that is has a pretty low value of the Q function. And what you can see here is that the algorithm has a really hard time finding three components. So it does, but it basically builds or makes a component that is what it's called here, number 1. There is this tiny component up here with just 2 or 3 observations. It can't really separate 3 from, so it merges these observations here that we know are a cluster of their own with some that are really members of a different cluster. So the quality of the solution is really poor. And this is just because, as we have been saying all along, there are different local modes for the algorithm. And in this case, it happened to converge to a local mode that was nowhere close to the global optimum. Let's discuss now numerically unstable modes. These are usually associated with configurations in which the model just utilizes a subset of the components and essentially gives very little probability to any observation belonging to some of the components that we allow in the mixture. Again, I'm going to illustrate this problem with the iris dataset that we have been playing with. And what I'm going to do here, so this code is very similar to the code that we have been using before. The only thing that I'm going to do different here is I'm going to initialize the algorithm in a very particular place. So the initialization for the weights is the same as always. We just give same probability to all the components in the mixture. In this case, there are 3 of them, as you can see up here. But what I'm going to do different is rather than initializing these means to random values, I'm going to initialize the mean of the first component as the global mean of the observations. And then I'm going to pick these other values for the mean of the second and the third as basically a shift on that general mean. And then the value of the variance for each one of the components is assigned in the same way as before. So remember, these are the initial values for the EM algorithm. Okay, so let's actually plot this just to give you a sense of why I picked those initial values. So these are the different components. The colors black, blue, and red just represent the two different components that we're playing with. And so what you can see is that the big dots, they're pretty big in this graph. So these big dots just correspond to the mean of the 3 components. And you can see that the first component is centered in the observations. That's what this choice of mu1 in the global mean does. But then by adding these shifts to the means of the components for the second and the third, what I'm doing is essentially centering them very far away from where the data is. You can imagine what the algorithm is going to do in this case. What it's going to try to do in this case is it's going to say, well, I mean, this component here actually represents the observations pretty well, but these are pretty far away, so there's going to be very little probability that I assign any of these observations to these other components, given those initial values. So let's see what the consequences of that are from a computational point of view. So what I'm going to do now is just run my algorithm. This is the same EM algorithm that I have been using always. And if you run it, you will see that you get an error in the algorithm, and that error comes from this piece of the code that is the one that checks convergence. And the error happens in the first iteration. So if you check the value of S, that just tells you which iteration you're in, this tells you that the error happens in the first iteration. If we want to see why, we can look at the values of the C's. So remember, C's is just telling you which component is being assigned, or which observation is assigned to each component. And we can see that essentially the algorithm, in that first calculation of the B's, is just assigning essentially everybody to the first component. That is the one that is centered where most of the observations are anyway. So, and it's essentially leaving these other two components empty. The fact that these two components are being left empty is what is causing the algorithm to fail, because then when you try to compute the logarithm here in the for the normal distribution, you start to get an error because you are essentially trying to compute the logarithm of 0 for some of the components. So that is the source of the problem. This issue happens with the EM algorithm. This issue does not happen with MCMC algorithms. And the reason for that is because when you're using a Bayesian method, the priors act as a regularization term and kind of correct the issues that come from having an empty component in the mixture. Now, in practice, this is usually not a very big deal in the sense that we rarely are interested in modes that look like this, modes where some of the components are empty, and those will typically not be global modes. But it may happen that as you run your algorithm, your EM algorithm, with different starting points, some of those starting points may converge to situations like this and may throw an error. And so what you need to do in those cases is directly discard the solution and just use a different starting value for your iterations. And that's typically a simple solution, but you have to be careful. The algorithm may fail not only because of the issues that we had discussed in the past, but also because it may be converging to a mode that leaves some of the components empty.